This is the second part of the videos on particle motion and integrals for February vacation. Go back to wherever you left off in your notes with this set of notes, and we're going to expand on it a little bit more, specifically on the integral of velocity, the integral of the absolute value of velocity, and the absolute value of the integral of velocity. They're all slightly different. We haven't really talked about this one much yet, so this is going to be new, and we haven't ever done this one by hand. You have most experience with this, not so much with these two. We're going to practice this in class, so your notes are going to be very, very helpful next week. Please pause the video, and after you wrote down these two lines, write or draw a careful graph of this, paying special attention to where it crosses the axes here. Okay, so hopefully that's all set in your notes. I have 3 columns here. In each column, we're going to be doing a different problem. There's this one, and this one, and this one here. So split up your paper into 3 columns, or however it'll work out well for you. And we're going to use the velocity graph 4 minus t is in feet per second for the first 6 seconds of movement. So remember, this is not the position, this is the velocity itself. Now we want integrals of velocities, some with absolute value bars in certain places. And what you have to remember is when you do the integral of velocity, that's the same thing as doing area under the curve of velocity. And the units are especially important when we interpret seconds times feet per second gives you feet, so it's something about position or displacement or movement. And we're going to explore each of these 3 here. Now for the first one, we just want the integral from 0 to 6 of velocity. That's basically signed area. We've been doing that geometrically a lot. Let's just do it algebraically so we can compare it to the other 3. So ignore these 2 columns right now and just listen in as I talk about this one here. In order to do the integral from 0 to 6 of velocity, I'm going to replace velocity with what it is. I'm going to use the first fundamental theorem of calculus because this is a definite integral. I have numbers at the bottom and top, and in order to do a definite integral, you just do the antiderivative and evaluate it at the endpoints and subtract. That gives me 6 feet. Now, if you didn't want to do it algebraically, what you could have done is just taken the signed areas, which are 8 from here, and -2 from here, added them up, and you would have gotten 6 as well. But we want to focus more on algebraically. Again, this is displacement here, and this means that wherever the particle started, it's 6 feet to the right of where it started. It could have gone left, right, back and forth 100 times, but wherever it was on the number line, it is now 6 feet to the right of it. Okay, so it started here and it finished here. So now let's talk about this one here in the middle. We haven't done this by hand at all. This is the first time you're seeing this, and we're going to practice it quite a bit this upcoming week. I want the integral of the absolute value of velocity. The absolute value is speed. There's no direction there. And when I do an integral of it, it doesn't give me displacement. It gives me total distance traveled. It takes into account the left and the right movement, and it adds everything up. So I need these absolute value bars. Are very important here, and I'm going to do the integral of the absolute value of 4 minus t dt. Now when I do the absolute value of v of t, remember v of t is this graph right here. When I do the absolute value of it, this part of it flips above the x-axis. So now I'm looking at this, and I would do a little sketch of this as well to help you remember what we're doing and why we're doing it. I'm going to be adding up these 2 areas. Signed area doesn't really matter right now. Everything's positive. This would have been negative, but visually what we're really doing is flipping it over and considering it to be a positive. So remember, 4 minus t has positive values and it has negative values. We want to split it up at 4. That's because that's where it changes from positive to negative, because we want to be able to split up the integral in the positive and the negative regions. So we're going to use one of our properties of integrals from that video. That was from a couple weeks ago now. And we are going to break up from 0 to 6 into 0 to 4 to 4 to 6. And you're definitely allowed to do that with integrals as long as this number and this number are the same. And very, very important here, I am subtracting these, even though normally you add them. And that's because the integral from 0 to 4 is just this right here, this area. It's already positive. However, this from 4 to 6, that's a negative quantity right here, but I want to add it on. The only way to think of it as adding it on is to subtract this negative amount, because subtracting a negative is the same as adding. So anything that would normally give you a negative signed area here, you're going to subtract it. Again, subtracting a negative is the same as adding. I can't say that enough here. So write that down, commit it to memory. And then what you're going to do is do the same old thing as usual. Do the antiderivative from 0 to 4. Do the antiderivative from 4 to 6, or evaluate it. So this is right here. And where am I? This one is right here. So hopefully you're going to pause and take a minute to think about this and make sure you're understanding what on earth is going on here. I took antiderivatives, I'm plugging in 4 and 0, subtracting, and then I'm doing the same thing from 4 to 6, plugging them in and subtracting. Notice there's always this minus here. So this is 8, and then I'm going to subtract this, which is 6 minus 8. So it's really going to be 8 minus 6 plus 8, which is 10. Now you could have gotten that if you had just thought of these as being positives and adding them up. But remember, we're not always going to have graphs, and sometimes you're going to need to be able to do without a graph, just algebraically. So the key here, I'll say it one more time, is to split it up wherever velocity changes from positive to negative. And you might be thinking, well, what do I do if I don't have a graph and I can't visually see? Well, what you have to do is set velocity equal to 0 and solve. So you could have taken 4 minus t, set it equal to 0. This is the easy one. T is 4. So you know that velocity is 0 there. Check that it changes sign. Some of them are going to be a little more complicated, but that's generally what you do. Now let's consider doing the regular old integral, which we did here, but then doing the absolute value. So we're doing integral first. What happens here is I'm going to do the regular old integral. Notice that these are absolute value bars. These are absolute value bars. This bar here is just the notation for the first fundamental theorem of calc. Okay, I took the antideriv. I'm going to plug in 6. I'm going to plug in 0. I'm going to subtract, and then I'm going to do the absolute values. Notice that in this case, the answer is the exact same. Like here it was 6, and here it was also 6. These two numbers will always be the same. It's just that this one's always going to be positive because it's absolute value. It's just like the first one. And this tells you that wherever the particle started position-wise on a number line, it's going to be 6 units or inches or feet from where it started. And because it's not positive or negative, like we took the absolute value of it, it could be 6 to the left or 6 to the right. We don't know which one, but it's 6 feet from where it started. And the way you could do that graphically is take the signed areas, add them, and do the absolute value. So it only really changes if velocity is negative more in some areas, and this answer was negative. Since this answer is positive, these are the exact same thing. Okay, so make sure all those notes are down. Look at those again. We're going to be practicing this in class next week, like I said, and very soon we're going to move on to brand new info. So we're almost done with the particle motion. Enjoy the rest of your break.